Every 60 seconds, the Pilbara's industrial heart moves over 1,000 tons of high-grade hematite. We are going 5.5 kilometers deep into this $200 billion iron ore engine, where 50,000 cubic meters of high-strength concrete stabilize the void. How does this mechanical titan defy geological limits while maintaining a perfect 24-hour autonomous heartbeat that never stops? The narrative of the Pilbara does not begin with the roar of a diesel engine, but with the silent precipitation of iron in a primordial ocean over 2 billion years ago. During the Neo-Archean and Paleo-Proterozoic eras, the Earth's atmosphere was largely devoid of free oxygen. Dissolved iron, leached from the crust by hydrothermal activity, saturated the world's oceans. As cyanobacteria began to produce oxygen through photosynthesis, this iron oxidized and settled onto the sea floor in alternating bands of iron-rich minerals and silica-heavy chert. These banded iron formations, or BIFs, eventually consolidated into the Hamersley province, creating the most significant iron ore province on the planet. For eons, these deposits remained undisturbed until the mid-20th century, when the Australian government lifted its iron ore export embargo. The discovery of the massive high-grade hematite body at Mount Whaleback in 1957 by Stan Hilditch transformed the region from a remote pastoral landscape into a global industrial hub. Mining operations officially commenced in 1968, requiring the construction of an entire town, Newman, and a 426-kilometer heavy-haul railway to the coast. This initial foray into the Pilbara set the stage for a half-century of engineering expansion, evolving from simple manual extraction to the current state of fully integrated autonomous megaprojects. The transition from the early mining of easily accessible high-grade hematite to the complex beneficiation of lower-grade magnetite marks the second great era of Pilbara engineering. Today, the focus has shifted toward the spec-heavy reality of maximizing recovery rates from increasingly complex ore bodies, such as those found at the South Flank and Iron Bridge projects. But as these operations push further into the Earth, what are the mechanical implications of maintaining such massive voids in the desert floor? The sheer scale of infrastructure required to support a modern iron ore mine necessitates civil engineering standards that mirror those of a skyscraper. At the South Flank project, which integrates with the mining area C-Hub to produce 145 million tons per annum, the foundation work alone is a monument to heavy industrial design. Contractors supplied 50,000 cubic meters of high-strength concrete to stabilize the primary crushers and conveyor transfer stations. This concrete must meet rigorous quality standards for heavy industrial use, often requiring high compressive strengths to withstand the rhythmic, low-frequency vibrations generated by the massive crushing circuits. Structural steel requirements are equally gargantuan, with 36,000 tons utilized for the ore handling plants and supporting modules at South Flank. Much of this steel is fabricated in modular sections to facilitate rapid assembly in the harsh Pilbara environment, where daytime temperatures frequently exceed 40 degrees Celsius. These modules must be engineered to withstand not only the operational loads of the ore, but also the thermal expansion and contraction cycles of the desert. The engineering objective is to create a rigid, zero-failure skeleton for a machine that will process billions of dollars of ore over a 45-year lifespan. But how does the mine maintain its geometry as it descends 600 meters into the bedrock? The 5.5-kilometer-long pits at Mount Whaleback and Sino Iron are not mere holes in the ground. They are carefully engineered geometric structures designed for stability and efficient material flow. The extraction process begins with the mapping of the ore body using advanced seismic data and exploratory drilling. Engineers then design benches or levels that typically range from 10 to 15 meters in height. These benches act as steps that allow massive machinery to navigate the pit while maintaining the overall slope angle, which is critical for preventing wall failure. The wall stability of a pit half a kilometer deep is monitored by sensors capable of detecting movement as small as a fraction of a millimeter. When a wall shift is detected, the mining plan is immediately adjusted to alleviate pressure. This is particularly vital because a single blast at the face can involve hundreds of tons of ammonium nitrate fuel oil explosives, displacing more than 1 million tons of rock in a single event. The force of these blasts shatters the rock into manageable chunks, which are then loaded by electric shovels and hydraulic excavators capable of moving 5,500 tons of rock every hour. What happens to this shattered rock once it leaves the pit? The material is transferred to a fleet of haul trucks that are, in themselves, miracles of mechanical engineering. These vehicles, such as the CAT 793F, have a gross operating weight of nearly 400 tons and a payload capacity of 240 tons. They navigate a network of spiral roads and ramps engineered with specific grades to optimize fuel efficiency and minimize wear on tires that can cost $30,000 each. But as the mine pushes deeper, the efficiency of this truck and shovel model begins to face the limits of physics. How do engineers bridge the gap between the pit and the processing plant? Once the ore reaches the surface, it enters a primary crushing circuit that marks the transition from mining to manufacturing. At projects like Sino Iron, the rock is fed into one of 4 7-story high crushers, each with a capacity of 4,250 tons per hour. These massive units reduce the ore from boulders the size of small cars to fragments the size of a house brick. The kinetic energy involved in this process is immense, requiring primary crusher foundations that are decoupled from the rest of the plant to prevent structural resonance. For hematite, the process is relatively straightforward, involving crushing and screening into lump, which are 10 to 30 millimeters, and fines, which are less than 10 millimeters. However, the rise of magnetite mining has introduced a far more intense processing requirement. Magnetite ore is often low-grade, requiring extensive beneficiation to reach the 67% iron content desired by the steel industry. This is achieved through a multi-stage grinding and magnetic separation process. At the Iron Bridge project, engineers utilize a patented dry grinding process that represents a step change in efficiency. Instead of traditional energy-intensive semi-autogenous grinding mills, the facility uses 12 high-pressure grinding rolls with a total installed power of 93 megawatts. These rolls press the ore with enough force to reduce 52 million tons of dry magnetic concentrate down to 80 micrometers. This material is then sorted by size using 12 massive 2-stage air classifiers, which eliminate the need for water in the initial classification stages, a critical innovation for an operation in the arid Pilbara. But how do you transport millions of tons of this fine, abrasive powder across 135 kilometers of rugged terrain? The logistics of the Pilbara are divided between 2 dominant technologies, the heavy-haul railway and the specialist slurry pipeline. The rail network is the traditional backbone of the region. The Mount Newman Railway operates trains that are over 2.5 kilometers long, consisting of 264 ore cars carrying tens of thousands of tons of iron ore. These trains are so heavy that they have their own gravitational momentum, requiring advanced braking systems and precisely engineered track grades to manage the kinetic energy of a 40,000-ton moving mass. For the new generation of magnetite concentrate, however, engineers have turned to hydraulics. The Iron Bridge project utilizes a 135-kilometer specialist slurry pipeline to transport its wet concentrate product to Port Hedland. The engineering challenge of a slurry pipeline lies in managing the physics of a 2-phase flow, maintaining a specific velocity to keep the heavy iron particles in suspension while minimizing the abrasive wear on the pipeline's interior lining. At the destination, the water must be removed, creating a paste-like material ready for the bulk carriers. At the port, the final stage of the engineering chain occurs. Port Hedland is the world's largest bulk export port, loading approximately 800 ships annually. A single bulk carrier can hold hundreds of thousands of tons of ore, and the loading process takes roughly 30 hours. The precision of the ship loaders and the synchronized movement of the harbor tugs ensure that this $200 billion export engine never stalls. But as the human element is increasingly removed from the cockpit, how does the digital nervous system of the Pilbara manage this complexity in real time? The most significant engineering shift in the last decade has been the total virtualization of the mining operation. Rio Tinto's Gudai-Dari mine is the industry benchmark for this Site of the Future program. It operates with a 100% autonomous truck fleet from day one, using 23 CAT 793F trucks that communicate via a high-speed network with latency under 50 milliseconds. These vehicles use LiDAR sensors that fire 1.3 million laser points per second to navigate their environment, effectively seeing in 3 dimensions with more accuracy than a human operator. The site also features a full digital twin of the processing plant. This is a feature-rich, interactive 3-dimensional environment that allows engineers to navigate the asset virtually, plan maintenance using 2-scale models, and download technical data directly from a tablet in the field. This connectivity extends to the drills and the trains. The AutoHaul system, the world's first fully autonomous long-distance rail network, is controlled from an operations center in Perth, more than 1,500 kilometers away. This remote operations center manages the movement of trains that have already traveled over 7 million kilometers autonomously, removing human error from one of the most dangerous links in the supply chain. Even the mundane tasks have been automated. Gudai-Dari utilizes autonomous water carts developed with Caterpillar to suppress dust on haul roads. These vehicles use intelligent onboard systems to detect dry conditions and apply water only where needed, reducing waste and keeping road surfaces at optimum traction. To power this digital infrastructure, Rio Tinto installed a 34-megawatt solar farm consisting of 83,000 panels, which supplies approximately one-third of the mine's electricity demand. But as the industry reaches for this high-tech future, it is frequently pulled back by the weight of its own capital intensity and the shifting standards of its social license. What are the consequences when the engine runs too fast? The financial stakes of the Pilbara are as high as the engineering demands. The South Flank project required a capital investment of $3.6 billion, while Fortescue's Iron Bridge project reached $3.9 billion. Despite these massive outlays, the return on investment can be rapid. South Flank achieved payback within 18 months of its first ore in May 2021. However, the road to these returns is often hampered by technical delays. Fortescue recently pushed back the full capacity target for Iron Bridge to 2028, citing the need for a more measured approach to ramp-up and operational efficiency. Beyond the balance sheet, the industry has faced severe criticism for its impact on cultural heritage. The 1920 destruction of the ancient rock shelters at Juukan Gorge by Rio Tinto serves as a permanent reminder of the risks of prioritizing production over shared values. The resulting parliamentary inquiry exposed critical flaws in company and regulatory systems, leading to a sweeping reform in how mining companies engage with indigenous communities. Today, engineers must account for cultural heritage and environmental stewardship with the same precision they apply to ore-grade and structural steel. As the industry looks toward 2030, the focus is squarely on decarbonization. Fortescue is testing hydrogen-powered haul truck prototypes, known as Europa, and autonomous road trains to reduce its carbon footprint. The goal is to transform the Pilbara from a source of raw iron into a hub for green metal production, utilizing the region's vast solar and wind resources to power the next generation of beneficiation plants. The 5.5-kilometer engine is not just digging for the present, it is re-engineering itself for a carbon-neutral future. If you want to see more of the incredible machines and massive projects shaping our world, hit that like button and subscribe to the channel. What part of this massive operation surprised you the most? Let us know in the comments below, and turn on those notifications so you never miss our next videos.